Yeah, in number theory. I remember in number theory you were doing this also. So, okay, so does everybody understand the idea? Yeah, sorry?
But we already have a proposition saying that singletons are closed, so why do we need to prove that?
Ah, you could just state the
Where
proposition.
is that from?
You're absolutely right. You could just state the proposition. I'm actually just wanting to show you kind of the level of something I might like you to be able to prove. So even though, so of course if you memorize this proof, you just write it down, but I would like to just practice. Let's say we forgot that we had a proposition. It is true. I'm glad to hear you've been studying that. So in any metric space, singletons are closed. Okay? But I want to prove that. Okay, so let's prove this for just the set X first. Okay, and to do this, we will show, you guys already gave me the idea, we will show that X minus the set little x is open. The complement is open, right? That's basically what we have to show. Okay, so this would make a nice question because you have to like understand how to show that something is open in a metric space. Okay, so how do you do that? What do we have to do?
Create a neighborhood.
Okay, neighborhoods are going to be involved. Can we be more precise? Like how do I set up showing that a set is open in a metric space?
For all x in x, there exists a p such that the neighborhood of x comma p. No.
I'm going to use y if you don't mind because I already got the x there. For all y and x, there exists a p. So this is for u open in x. So actually what you mean is
In u.
for all y and u, right? There exists a p greater than 0 such that. Okay, good. So this is a nice reminder of a very important definition here. This is in a metric space. This is what an open set is. Of course, in chapter 3, an open set is just anything in tau, right? In the topology. Okay, so this is what we would want to prove right now. Okay, so here is my set U right here. So for all y in U. So to prove what this blue part says, I'm going to let y be an element of that set x minus little x, which is really just saying that y does not equal x, right? So y does not equal x. Okay, so we pick a point that's like that. I guess I could draw it over here. Here's the y not equal to x. Okay? All right, so can somebody tell me how to come up with the radius p for this? Same?
You can make it the distance between y and x.
Okay, and you guys you can define what the p is going to be, right? So it's just going to be the distance. We have a metric here. The distance between y and x. Okay? And then you've produced a p, but you should also show me that that p works. So your claim at this point, okay? So this is where, by the way, during the test, if it's not clear what you need to show, just come ask me. I'm going to be here, of course. Like if you think that you can just stop here and don't have to finish the proof, you might check with me and I'll let you know, no, I think you should show that your p really does work. We would want to claim that this neighborhood is contained in x minus the set little x. Okay. So we actually have to pick something from here and show that it lives here. Well, the key to doing that is to just note that if z is in this neighborhood, then the distance from y to z is less than p, just to kind of remind you what that means. And that means that z does not equal x. Because if z was equal to x, then this distance would be equal to p. Yeah, by the way, you have to think about what's your goal here? your goal is to show that Z lives here. Well, living here just means not X, not little x, right? So you just want to show that Z is not little x. That's exactly what you got there, right? So Z is in capital X minus little x. This little one line in blue justifies that claim very nicely. Okay? So thus, X minus little x is open. So the set little x is closed. And now capital F is just a finite union of closed sets. Okay, so thus capital F is closed. It's a finite union of closed singletons. You know, one of the things that I think is kind of hard about a class like this, aside from just the material, is kind of knowing, like, what are you totally expected to write up? Like, if you didn't put this part in parentheses, would it be okay? Or you have to write that down, right? I mean, you had so many different professors while you've been a student here, and each professor is a little different about what they want. It can be kind of tough. Like, I've been in your shoes. Like, I know what that's like. Of course, my best advice is always that if you have the time, you know, it's better to over-explain something. You know, put the comment in there rather than omitting it, because that way, you know, you make it more clear that you know what's going on. But again, I'm just going to say, if something is clear, like if you left out, in this case, if you left out the part in parentheses, I would not take off any points for that. Because to me, it's clear that capital F is a finite set, and if you're taking a finite union of singletons. I can see in my mind that's how you're doing the problem. Okay. But again, if you have any doubt during the test, oh, do I need to like justify this or that or whatever, you can come ask me. More than likely, if it's something that's, that you're justifying that's really something we learned here in 414, I'm probably going to say, yeah, I think it'd be good for you to give me a couple of sentences or a quick little reason why. If it goes back to like 3 semesters ago when you were like a sophomore and you learned some basic thing about sets in Math 280 or whatever, I'm probably going to say, you know what, that's not what Math 414 is focused on. You don't need to like, you know, re-convince me of something that's kind of elementary. So, but use your best judgment on it, and definitely feel free to ask me during the test. It's not, it won't bother me if you come up and ask me questions during the test if you're not sure. Okay? Okay, so that's that one. Okay, let's do, yeah, Alex?
Instead of doing one singleton and then taking the union,
Yeah.
if we wanted to like just make it
I,
arbitrary,
yeah, you could.
would you make a, would a neighborhood that would work would be?
I know what you're going to say. Yeah, so suppose you just wanted to take the whole finite set F to begin with. Right. So if that's what you were going to do, then you would pick an x that's not equal to any of these.
Yeah.
Go ahead. And then what would you choose P to be?
The minimum of all the distances between x and those individual.
Between y and each of those. Yeah.
Or yeah.
You don't have to be defined, right?
Pardon?
You don't have.
Oh, that should be a distance. Sorry.
Yeah, yeah.
Sorry. Distance between y and x1. At this point, I can just, if I make any mistakes up here, guys, I can just claim, which is true, that I've been up since 4 in the morning in Texas. So anyway, yeah, that would be the better thing to say. Why wouldn't this work if you had an infinite set? Why couldn't you just go ... infinitely far? The minimum of an infinite set could be a problem because you could actually have a minimum that would be like, it's actually an infimum, which could actually be 0. And in that case, your P is not greater than 0 and it wouldn't work. Right? Okay, great. Let's do another one. So some problems just on metric spaces, some problems on topological spaces. Okay, let's do number 3 here. Let's do a problem that combines metric spaces with topological spaces. Okay? So let's let X be the set 1, 2, 3. And let's let tau be the set that has the empty set, capital X, and 1, 2. Does everybody agree that that is a topology on X? That should have been one of your 29 topologies you wrote down when you did that one problem, right? Okay, here's what we're going to do. I would like to prove that tau is not induced from any metric D on X. In other words, there is no way to make a metric on X whose open sets would be exactly these. Such that, now an open set in a metric space is just a union of neighborhoods, right? That's one thing we learned. So I claim that there's no way to put a metric on this set in such a way that the unions of neighborhoods that you would make would give you exactly these 3 things. Of course, you have the empty union here, and then somehow these would be unions. I'm claiming this is impossible. To have just that only. So remember, for example, if just to give you another example to help you think about this, if your topology had been, this is just scribbling, so you don't have to write this down, but, and I've already talked about this before, but if this had been your topology, this topology is induced by a metric. This is the discrete topology. Every single subset of capital X is included in tau. Do you remember what the metric is that creates this topology?
The one if the points are equal and 0 or not.
Exactly. The distance between any 2 points y and z is 0 if y equals z, and 1 if y does not equal z. The idea is there that if you take a neighborhood around, well, excuse me, any one of the elements of X of radius a half, what things are in that neighborhood, what points are less than 1/2 away from 1? Just 1, right? So actually, your neighborhoods are just singletons. And then if you take unions of singletons, you get everything. You can make everything out of it. So this topology is induced by a metric, right? What we're trying to say here with this problem is show that this topology, which is also a topology, but that this one would not arise as a result of putting an appropriate metric onto a space. It's kind of a tricky kind of problem because you're like trying to show that you can't do something. Like that you can't put a metric on a space. Like, well, why not? I could try, who knows how many different things I could try for a metric that might work, you know. But somehow it won't work. So I'm wondering how we could do this. One of the requirements of a metric is that the distance between any 2 different points has to be greater than 0. Right? So, you know, the distance from 1 to 2, the distance from 1 to 3, and the distance from 2 to 3, they all have to be, you know, positive numbers. So, Does that help us at all? Let's suppose by way of contradiction that we do have a metric on X, right? Suppose D is a metric on X. You've got a metric there. Your open sets then are going to be neighborhoods, right? So I'm going to create a neighborhood that's none of these three things. And therefore, you have an open set, because the neighborhood is open, right? You're going to have an open set other than those three things. How could I do that? Does anybody see, how could I make a neighborhood? So if I'm going to make a neighborhood, I have to have a point and a radius. How can I make a neighborhood in this is not a very big space, in this space? So I have to create a neighborhood around one of these 3 points with a certain radius. And, you know, how could I do that? So the point is 1. You want to use a 1/2 here? Any fraction like that? Okay, so what's this neighborhood?
1.
Well, what if these points are 0.2 apart? I just said suppose there's a metric. I'm not saying it's the discrete metric that we were looking at before. What if you know? What if the point 1 is right there and the point 2 is right there, and then you make a neighborhood of radius 1/2? You know, while 2 is inside there.
Or is it possible to take, let's say you want to find a radius? Is
Yeah.
it possible to take like the middle of those D's and then divide it by some number so it's like smaller and it doesn't touch anything?
Actually, you don't even need to divide by anything.
Oh, okay.
Yeah, because because the neighborhood consists of points that are less than p units away. Yeah, what I would do for my radius here is just make it whatever the distance from 1 to 2 is specifically. I don't even need to worry about the other ones. So this is how far apart 1 is from 2. So notice that this neighborhood, I don't actually know what all is in this neighborhood, but I know that it contains 1, obviously, because it's centered at that point, but does not contain 2, because 2 is too far away to be in I've chosen a radius here that exactly excludes 2. So I have to have an open set, right? I have to have an open set now. This is an open set that has 1 in it, but not 2. But our topology has no such set. Any set that has 1 in it also has 2 in it, right? Okay, so, however, tau contains no such set. Yeah, Zane?
Could you also have done a neighborhood centered at 3, and then whatever your P is going to contain 3, which is in our topology?
Yeah, I could have done that as well, right? This one would work if there was no 3 in the problem at all as well.
Yeah.
So, yeah, it's a good one. Yeah, Sarah?
So is the distance between 1 and 2 is the same as the distance between 2 and 3, which is equal to 1?
No, we don't know what the distance is.
Oh.
These are not even, I should have called X, A, B, C. So you're not thinking about numbers, right? They're just 3 arbitrary objects.
I thought we're using the real numbers.
No.
1, 2, and 3, that's why it says-
No, this is Sarah, Mackenzie, and Dr. Hannon, right? We don't know how far apart we are, right? The distances are like arbitrary, it's like whatever. Okay. Yeah, so I thought that was a nice little problem. Let me just do a couple more things here. Oh yeah, I think we need to practice a couple more things. How are you guys feeling? Do you feel like, gosh, you know, these are reasonable, or is it just, it is also late, so, you can handle these kind of things?
I feel like you've given us hints on all of them, and I feel like I haven't come up with any of the answers on my own.
Well, you know, it's also partially that, you know, when you're in a big room with like 12 people, it's like boom, 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 and
Yeah.
who's gonna come up first with it? So, don't let that be a point of discouragement, because you're gonna have more time on your own thoughts, you know, without being interrupted. I think that might be part of what's going on as well. Okay, let me do this one. So, what number am I on? Number 4? Yeah. Okay, let capital X be the set of functions from 0, 1 to 0, 1 with f continuous. All right, and then define d of fg. So the distance between two functions, I'm going to give you a new expression here. The absolute value of f of 1/2 minus g of 1/2. My question is this a valid metric? Is d a valid metric? Okay. So I'm going to give you a minute to think about this one for a second. Again, probably on the actual test, I wouldn't ask it like this. Because this is basically equivalent to true-false. I would probably be more likely to say, this is a metric, show it, or this is not a metric, show why not, right? But for now, since we're still practicing, you know, this is something I want you guys to think about. Take another minute. I'll let you guys think about whether, first thing is just get an intuitive idea whether you think it is or not. And then you can think about how you would proceed. You have to know your axioms of a metric, of course, and play with it a little bit. Let's just do a quick little show of hands here. How many people think that it is a valid metric? A couple people. How many people think it is not a valid metric? Okay, so about twice as many people saying no. I always like to talk to the people who say no, because then it's easier to figure out, so what's wrong, you know, and try to give an example. Is there a particular axiom that seems to be a problem? For those of you who think it's not? Mackenzie?
3. Axiom 3.
And axiom 3, just to remind myself, that's the one that says the distance between f and g is 0 if and only if f equals g. So this one has a problem, so you think there's two different functions that have a distance of 0. Can you give me an example?
I used f equals x then
Okay.
G equals 1 minus X.
So those two functions right there, they definitely, on this domain, they're definitely continuous, right? They're in X for sure. So this is in the space. And I agree, because f of 1/2 and g of 1/2 are both the same. So in this case, the distance from f to g is, so this you could just, I mean, well, you could write it out, I guess. Absolute value of f of 1/2 minus g of 1/2. Or you could literally, if you just wrote equals 0 here, I would take that, because it's pretty clear, right? F of 1/2 is obviously 1/2, and g of 1/2 is obviously 1/2. Like, this is all just totally unnecessary to write all that stuff down, but that's fine. Okay, so that equals 0, but f does not equal g. Exactly. So that would be a great justification. Okay, so the answer here would be no. Okay, so that's good. So I just wanted to review I've got a couple more of those, but I think I'm going to skip them for now, because I think you guys have the idea about how to do those kind of problems. So that's that one. Okay, let's go on. Is everybody okay with that? All of the yes people are convinced it doesn't work? Okay, great. And let's do another one. Let x tau be a topological space. Assume capital A is an element of tau, and let the set of B sub i's, such that I is in capital I, be a family of sets in capital X, such that x minus b sub I is in tau for all I in capital I. So this takes a little bit of writing. So you have one set that's in tau. You have a whole other family where every complement is in tau. And then I want to show that A minus the intersection, where I is in capital I of B sub I, is in tau. So I wanted to at least put one thing in the review that kind of goes back to chapter 1. Does this kind of look familiar? Subtracting sort of an intersection of arbitrary sets. Do you guys remember how to rewrite it?
The union of A minus B sub I.
Right, it's the union. So that's the idea here, is that this is the union, where I is in capital I, of A minus B sub I specifically, right? So that's, you can just say, by the way, something like on that, if that comes up for you, you can just say by chapter 1 homework. By the way, I never will expect you to remember which homework number or which problem, or even like if it's by a proposition from class and you don't remember the number, it's okay, right? That's totally unimportant to me. So you can just make references like that. Just make sure it really was something that we did. I'm pretty sure we don't want to be making things up. But anyway, so that would be a good first step right there. Okay. Now, we're trying to show that this thing is in tau. Tau is a topology.